I'm Alex. I'm a postdoc from just down the hall here. I'm working on basically all things to do with hidden companions to wobbling stars using gyroastrometry. I didn't really have the space to fit all that in on this first slide. I'm working with Andy Casey here at Monash. So first of all, the basic stuff first. Basically, if you have a binary star or star with any companion, you get this wobble. They're actually orbiting around the center of mass, the barycenter here. And if they differ in brightness, there's also a photocenter, which is not necessarily in the same place, the center of mass. And so we get this motion throughout the orbit. Photocenter goes around the barycenter. And what we're mainly interested in is the difference between these two, because this is what causes our wobble if we have a companion, where the Q and the L there are the mass and light ratio, respectively. So in this talk, we'll keep it simple for dark companions, by which I mean companions where the basically the luminosity is negligible compared to the primary star. L is 0 or thereabouts. So this talk will mainly be focusing on these dark companions. But the motion is actually a bit more complicated than that. So if we have a single star, there's no wobble, but it does have a parallax. This particular example also has a proper motion going to the northeast. So over the course of 4 years, I think, is this video, it's going back and forth of a parallax, and it's also moving from its starting position. But if we add a companion to this, in this case, it's a dark companion. They're both orbiting around the center of mass given by the dotted line, which is following the single star track. And whereas the blue luminous star up there is the photocenter, and that's, as you can see, going in a slightly weird track there. So if you could observe this continuously over those 4 years, that's the kind of thing you'd see, which doesn't really resemble the single star track at all. But what we have with Gaia, which makes things a bit more complicated, is that Gaia is constantly spinning. It's seeing these stars in sort of snapshots. That's all dictated by the scanning angle, which is basically the angle that the field of view of Gaia is moving relative to north. And so here on this plot, I've added exactly where Gaia would be observing this particular star. Should say this star, the proper motion and parallax are real, and I've added a companion just through simulations to make this a bit more obvious. But in this example here, the arrows indicate where Gaia is observing it, and they're pointing in the direction Gaia is scanning. So we end up with this one-dimensional astrometric signal, which I'm calling XAL for a long scan direction. Which is just given by the offset in right ascension declination multiplied by the sine and cosine of the scanning angle. And so we end up with this as the Gaia observations, which I don't actually have access to yet. I'll get to that later in the talk. So we end up with, so like I said, a one-dimensional time series of astrometric observations here. And what we want to do, what Gaia does first, is try to fit that to a single star. So assuming there's no companion, but everything's going okay, we then want to calculate the parallax and proper motion of this star. So here I've got those actual observations and the fitted track there. So you can see there are quite a few differences along there. And if we were to plot that out on a two-dimensional sky, so the orange one is the track that we've fitted. Obviously, it's quite different from what's actually going on, because what's actually going on is not a single star. So that's quite a bad fit, and we're really interested in is how bad is the fit. So now we get into the realm of astrometric errors. So we take that that simulated track. We've got a parallax, proper motion, and position, and we want to calculate the expected position along the scan based on these fitted parameters, which is given by this matrix equation. I'm sorry to bring up all these equations so late in the day, but we have this matrix A, which is an n/5 matrix, where n is the number of our observations, and it's simply the sine and cosine of the scanning angle, and this very long term, which depends on Gaia's position at various times, and that basically tells us how the star's position changes depending on the parallax. And then the last two terms in that matrix refer to the proper motion. So we can now calculate a difference between that expected position and the observed position, which I'm calling R there. And now I produce the important number, the reduced unit weight error, or RUI, which is sort of like a chi-squared. Just sum up all the squares of this differences, divide by the number of degrees of freedom, because we're fitting 5 parameters at n-5, and it's all divided by the sigma squared, which is generally of the order 0.1 milliarc seconds, but it sort of varies from star to star. So this basically tells us sort of how significant are these differences relative to the errors. And so if we had a proper distribution of single stars, this RUI value would average about 1. So if it's anything more than 1, general rule of thumb is about 1.4. It's generally a clue that something weird is going on. But what my work is mainly concerned with is finding orbital parameters. So you've probably seen this diagram from Wikipedia before. So there's quite a lot going on with orbital parameters. It's not just all about periods and masses and things. There are all these angles that we have to consider as well that could be affecting the astrometric signal. So what we do in this method is we create a model that calculates the expected photocenter position as a function of time and all of these parameters. And from this, we can actually predict the RUI based on the method I showed before, and what the fitted track parameters would be based on all this. And then we use STAN to find the posteriors of these parameters using Bayesian inference. And what we want the parameters that we want to fit mainly are the mass of the primary, mass of the secondary, period eccentricity, all these angles, and time of periastrum. So that's quite a lot. But there are some other parameters we're also trying to fit, which are the offsets in position, the parallax, and proper motion. And the reason we fit these as well is because basically the fitted track parameters that we get from Gaia, we know that there could be something wrong with them. So what we're trying to fit is the real parallax and proper motion, so the actual motion of the center of mass in this case. So I don't really have time to go through everything that we did with this. So I'll take a particular example, which is exoplanets, which is sort of, that was one of my favorite areas to go in. It's what I did my PhD mainly on. So going straight in there with a rather challenging example. So here's a plot of a lot of the exoplanet discoveries over time. I think it's like almost 6 months out of date actually. But this is sort of the region that Gaia deals with in period space. The actual mass range can vary according to all sorts of factors. So it's a similar range to radial velocity, but the advantage of over radial velocity is that it's mostly independent of the inclination of the system. So I'll pick one of my favorite systems here. This is Beta Pictoris. It's a rare edge-on system that's been directly imaged, and this has a RUI of 3.07, which is reasonably high. So before we go into all the Bayesian posterior stuff, we can actually plot out to see how the RUI varies as a function of mass and period. This is assuming the 90-degree inclination, so it's an edge-on system. So you can see the RUI would obviously increase if you had a more massive planet. It's more of a wobble. And then it peaks at this period of about 3 years, which is simply the amount of time that Gaia has been, or the length of observations that we have for this system. And so that dotted line there is 3.07. So we would expect to find the planet mass and period somewhere along there. But as it turns out, the planet shown in the on the left actually is all the way out there. So it's got a period of about 28 years, I think, or 23 years. And according to this plot, that should only give a RUI of a bit more than 1. But as it turns out, there is a second planet that's been discovered through interferometry, and that if considered on its own, ignoring the other planet, should give a RUI of almost 3. So so there's strong evidence that this RUI of 3.07 is caused by these two planets working together. So what we do in this model is we actually only assume there's one planet, and we can plot the posteriors out there. I'm not showing everything that we're plotting, just just for simplicity. And so we got mass peak at 16 Jupiter masses there, but you can see the angles are sort of all over the place. And if we combine it with images that we have of this planet, such as that, so now we're actually feeding images in there as well. We're not just using the RUI signal from February to December there. And now we get a much better posterior distribution there, with a peak much closer to the 10 Jupiter masses we expect. And now we've got a period more tightly constrained, and all the angles are very tightly constrained, and that's because the calculation of omega there is trivial. It's just a line there. So in the future of Gaia, we so the problem is that we're now reducing it to just the one value, the RUI, whereas the next data release should actually contain all this epoch astrometry. So how will this improve our results? So here I've simulated a system similar to beta pic, but now it's no longer edge on. Yeah, so same location, 3.5-year orbit, and the inclination is 65 degrees, and we produce that sort of signal with RUI similar to beta pic. And then if we don't use any of the epoch astrometry fed into our models, we get something like this, where the angles are still a mess. But if we actually had access to all this time series data, then we get something like that, which dramatically improves all of it. So if we can compare those two, you can see, just using that 1D time series data has dramatically improved our results there. But the thing about the next data release, it's actually not going to just be those 3 years. It's going to be 66 months or 5.5 years, which produces that sort of signal there. And the RUI has now increased to 4.45. And now we get that. So this isn't using any imaging data. It's purely simulated, so it's a bit speculative still. And so we can now basically constrain all these. They're not exactly on the true values given by the blue bars there, but you can see they're now much more tightly constrained than they were when we were just using the RUI. So I realize I've gone a bit over time. I was afraid of that. So I'll just go with the conclusions. So the point of all this study is that RUI suggests the presence of hidden companions, but it's a bit difficult to actually constrain the parameters. So here I've got a plot of nearby stars and their RUI. So there are, most of the RUIs are quite low, around 1, but there are some that potentially targets of interest there. So we can mainly infer the orbits when you combine it with the other methods, such as imaging or radial velocity. And we've shown that 1D time series data will greatly improve the results. And perhaps most importantly is that this method can be applied to any other type of companion. So not just planets, if that's not your thing. We can also go with stellar binaries, black holes, neutron stars, and so on. Yeah, I'll stop there. Thank you.